Hello, thanks for coming back for the second part of 4.1. We're talking more about probability. And we are on the bottom of page 371 here. And it says probabilities are usually expressed as fractions or decimals. We talked about that earlier. That's what that's going about. So it says, describe exactly what you think it means when a weather forecaster says that there's a 10% chance of rain today. So there's I have a couple different theories on this, but maybe 10% of the viewing area will get rain. That's my guess. A lot of people think that a 10% chance of rain means that it will rain for 10% of the day, but that's not correct. The forecaster is expressing a probability, how likely he or she thinks it is that there will be some measurable precipitation in that area today. So in a sense, it means that if you keep track of 10 days with a 10% chance of rain, you would expect rain on one of the 10 days. Estimate the probabilities of each event occurring in your life. You don't have to do any calculations. So these are just things you're going to assess for yourself. What is your likelihood of passing this course? You should know that by now, especially monitoring your work in JetNet and Alex. What is your likelihood of living past the age of 100? Maybe 5%. I don't know about that. Your likelihood of winning the $1 million lottery, very, very small. What about your likelihood of doing tonight's homework? I hope that's pretty high. Okay, it says sometimes it's useful to find the probability that a given event will not occur. Here's an example. What's the probability of rolling a 2 with one die? So we said that occurs, the probability of X equal to be a 2 is 1 out of 6. How many outcomes are in the event of not rolling a 2? Well, that would be the other 5, right? Use your answer in question 7 to find the probability of not rolling a 2. So probability of not a 2. So we could say 1 minus 1 over 6, which is 1 minus the probability of a 2. That's another way, because we did that in our mind, but that's because we only had 6 options. And this is called the complement. So on the bottom of page 373 is the complement of E. When you roll one die, you will either get 2 or you will not. If we call the event of rolling a 2 E, then we call the event of not rolling a 2 E prime. That's what that's called. And we read it as E complement, the complement of E. For an event E in a sample space, the set of all outcomes that are not in E is called the complement of E. So describe the complement of each event in detail. Don't just put not in front. Think hard. So passing this course. So the complement of passing this course is the probability of failing the course. That would be the complement. What is the complement of winning $1 million when you buy a lotto ticket? The likelihood, or you might want to say probability, of losing your money on the lotto ticket, which is very likely because you're not likely to win. Okay, so for any event E, E complement is the event E does not occur. So 1 minus the probability of E. So that means the probability of E plus the probability of E complement should equal 1. Something to think about. Okay, so number 10 says, of the next 32 trials on the docket in a county court, 5 are homicides, 12 are drug offenses, 6 are assaults, and 9 are property crimes. If jurors are assigned to trials randomly, what's the probability that a given juror won't get a homicide case? So probability of not homicide. What is the probability that a given juror won't get a homicide? So you could do 1 minus the probability of homicide, which is 1 minus, and they add, they're out of 32, there were 32 trials, and the homicide, there were 5 of them. So that means 32 over 32 minus 5 over 32 is 27 over 32. Or you could just add up all the ones that are not, which would be 12 plus 6 plus 9 out of 32, which is also 27 out of 32. That's another way you can do it. Okay. So the second kind of probability that we're going to work with is called empirical probability. This type of, it says the second approach to probability we will study is computed using experimental data. So that's the key, is you actually run an experiment rather than counting equally likely outcomes. For example, suppose that out of the last 100 days, you've gone to the gym 60 times. It would be reasonable to guess that the probability of you going to the gym on any given day is about 60%. This type is called the empirical probability. It's based on observed frequencies, observed counts. So let's look at 11. On any given day, there are exactly 2 possibilities. You go to the gym or not go to the gym. Why would this fact and theoretical probability not be useful in deciding the probability that you'll go to the gym? Because theoretical, because it is not equally likely 50% that I will go to the gym. It's only 40, 60, right? 60% that I will and 40 that I won't. When calculating theoretical probabilities, we assume that all outcomes were equally likely, but there are plenty of situations where that assumption would be faulty. In that case, we often perform an experiment to estimate the probabilities. If you flip a paper or plastic cup, it can land on its top, its bottom, or its side. Are these outcomes equally likely? No. I would guess maybe on its side would be more, but I don't think it's all equally likely. What about estimate the probability of each outcome? I don't know. I guess you're going to have to take your guesses. I'm guessing on its side is higher. And it's probably heavier on the bottom. So I would maybe guess top face down would be maybe 20% on this, on it, the paper cup side. I would say is probably 50%, and on the bottom face up would be 30%. I'm just guessing. So if anybody knows, and if you play Tippy Cup, then you can send me what you think the likelihoods are. Okay. So the way that we estimate the probability that you go to the gym on any given day is a good model for how to compute empirical probabilities in general. And it's similar to what we did in the first part of the lesson, but it's the observed frequency of the event, or the number of ways that it happens, out of the number of trials. So it says, describe how you could design an experiment to develop empirical probabilities for flipping the cup. So we could take 10 cups and flip them, right, and see how they land. But we have to make sure, and we can mix it up with lots of different people doing it. So different skill levels, that would be important, right? And then you'd have to tally how this would happen. So I am not going to do that, but that's what you would do. So the table that you would organize with these tally marks of how it landed would be your frequency distribution. This is a table that lists categories that we call classes. In this case, the outcomes of the experiment and frequencies for each class. Okay. So complete a frequency distribution for going to the gym based on the data given earlier. So on the 50 days, we said going to the gym would be 60 times. So it would be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We'd have to do this 60 times, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's 20. 1, 2, 3. That's 30. So there's 10, 20, 30. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's 50. 1, 2, 3, 4, 5. There's 60. Oh, 10, 20, 30, 40, 50. There's our 60. And it's going to total 100. So then our observed frequency of not going to the gym would be 40. So that's the idea that we are getting at. So in a random sample of 500 people, 210 had type O blood, 223 had type A, 51 had type B, and 16 had type AB. Set up a frequency distribution for this data. So we would have O, A, B, and AB. And we would have 210, 223, 51, and 16. So when a blood transfusion is needed in an emergency medical situation, you might think that you'd have to receive the same blood type as your own, but that's actually not the case. This chart describes which types can donate and receive various blood types. So O is the universal donor. They can donate to everyone, but O can only receive itself. That's really the interesting part. And then AB can receive everybody, but they can only give to themselves. And then A can go to A and AB, and B can go to B and AB. What's the probability that a randomly selected patient can receive only one type of blood? Oh, geez. So they can only receive one type of blood. So O can only receive one type of blood out of the 4. <clears throat> 19 says, if an accident victim has type B blood and an EMT on site is the only person willing to donate blood, what's the probability that it will be compatible with the victim? B. So back to 18 per just a minute. So 1/4 of the time, they can only receive one type of blood, and that is AB can, O can only receive themselves, right? Type O. And then for them, that is 210 out of the 500 people, right? So of the 500 people, there's 210 of them. So 42% of the people can only receive one type. So here we're saying type B blood, what's the probability that it will be compatible with the victim? So type B can receive from B and O. So they would have to be the probability of O or B. So O would be the 210 people plus B would be the 51 out of the 500. So 261 people out of the 500. So 52.2% of the people could donate to them. If a person with blood type A gets a transfusion, what's the probability that the donor was not a type A? So we are looking for A complement. So we can say 1 minus the A, which is 1 minus, and A was what's probably that the donor was not a type A. So, and they got the transfusion. So the only people that A can get from are A and O. So it can't just be this. It has to be O, because they're the only people that can donate to A besides itself. So that would have to be 210 again out of the 500, which is 42%. Find the probability that a randomly selected donor's blood can be given to patients of more than just one blood type. So everybody can give to more than one blood type except for AB. They can only give to themselves. So that would be the probability of AB complement. So 1 minus the probability of AB, which is 1 minus the 16 out of the 500. So this one is definitely not a clear-cut set of questions. So don't worry, I give you ones that are a little bit more clear-cut. So 96.8% of the people can donate to more than just one blood type. Okay. So it says we're going to close the lesson with a comparison between the two types of probability we've studied, theoretical and empirical. The key thing to remember is that in theoretical probability, we use a sample space with a definite number of outcomes and assume that all of them are equally likely. This makes theoretical probability a bad option for something like the probability of a team winning a given game, because in most cases, it would be silly to assume that who wins a game is random. Empirical probability, on the other hand, uses observed frequencies and a total number of trials to compute a probability. A perfectly reasonable question is, how many trials are needed to get an accurate probability? The answer, of course, is 7. Just kidding. There is no answer to that question. All we can say is that the more trials you do in an experiment, the more likely it is that the probabilities you calculate are true representatives of the situation. The distinction between theoretical and empirical probability can sometimes be pretty subtle, and it may depend on the exact probability you're interested in. For example, suppose that you buy a bag of M&Ms, which is always a good idea, and you find that 50 of the candies are in the bag, 10 are brown. You could conclude that the probability of drawing a brown M&M for that particular bag is 10 out of 50 or 20%, and that would be a theoretical probability. But wait, you say, isn't it based on observed frequencies? Well, yes, but since you know for a fact that there are 50 total outcomes and 10 of them satisfy the event, picking a brown candy, then you're using theoretical probability formula. But if under the same circumstances, you conclude that there's a 20% chance that the first M&M you pick out of the next bag you buy will be brown, now it's an empirical probability because you're using the observed frequencies from that one bag to predict probabilities for a general situation. So you might find it helpful to think, are we using a number of all potential outcomes? If we are, you're probably looking at theoretical probability. Okay. So decide if, on the last 4 questions, we're going to decide if theoretical or empirical probability was most likely used to get the given probability. The probability of a high school basketball player one day being drafted by an NBA team is this. And they're not all equally likely outcomes, right? So it would have to be empirical. The probability of being dealt one pair is in 5-card poker is this. So they are based on equally likely outcomes. Even though this is not equally likely, they're based on the original likelihood of drawing a card is 1 out of 52, and they're all equally likely. So they're based on theoretical probabilities. The probability of being in a fatal accident if you make 2 car trips a day for 1 year is this. Again, empirical. It's based on collected data from real life. And the last question says, the probability of winning some prize when buying 1 New York State lottery scratch-off ticket is this. And this is based on equally likely outcomes, but because they only print so many, right? So they all could be chosen, but I would say this is empirical because not every scratch off has the same likelihood. So I guess every ticket is as likely that you would purchase that one that is the true one that wins. So I think maybe it's based on original theoretical outcomes. That one's a tricky one on the way you're thinking about it. That one's a tricky one. I would say you could think about that both ways, empirical or theoretical. But your likelihood of actually getting the one is definitely not high, right? Okay, so come back. We are jumping to lesson 4.4, and you're only 3 lessons away from 4 lessons away from finishing your semester. So we'll catch you back.